We've seen already that it's impossible to influence the position of a solubility equilibrium by adding or removing solid, since solid doesn't appear in the equilibrium expression. The issue is that adding or removing solid does not change the value of Q relative to K, and so if we're already in an equilibrium state, we will remain in an equilibrium state even if solid is added or removed. So that raises the question of how do we outsmart equilibrium when we're talking about solubility equilibria. Using the solid, using the reactants, is basically off limits. Instead, we need to think about manipulating the concentrations of A plus or B minus to influence the position of a solubility equilibrium and push it, for example, back towards the reactants or more towards the products. In this video, we'll talk about the common ion effect, which is a great way to push a solubility equilibrium back towards reactants through the use of a common ion, an ion that is common to both a salt of interest and a salt that we've added to a solution of a different, for example, cation. So we saw previously that adding or removing solid will not affect the position of a solubility equilibrium for the reasons just described. But what happens when we add an ion by dissolving a different salt that contains one of the, say, two ions in a dissolved salt? Let's consider Le Chatelier's principle and think about what happens when we dissolve a salt containing an ion in common with a different solubility equilibrium. So let's imagine that we had solid barium sulfate in equilibrium with aqueous Ba2+ and dissolved SO4 2-. Let's imagine that we start an equilibrium such that Q is equal to K, and we spike the solution with sodium sulfate, Na2SO4. Most important for the purposes of the barium sulfate equilibrium, what we're doing when we spike with sodium sulfate is we are introducing sulfate anions into the solution and increasing the concentration, very rapidly in fact, of sulfate ions. What effect does this have on Q? Well, this is the addition of a product in this equilibrium, and so the result is to increase Q to a point greater than K. The only way for Q to return to the level of K is for some of the products to go away, some of the products to return to their reactant form. And so the addition of that SO4 2- causes additional precipitation of BaSO4 solid. This effect, the effect of an ion in common to two salts pushing a solubility equilibrium back towards the solid state, is known as the common ion effect, because the SO4 2- ion in this example is common to both the spiked salt, Na2SO4, and the salt whose equilibrium we're interested in, BaSO4. The presence of SO4 2- in solution after the spike causes this reaction to move towards reactants. This is just an incarnation of Le Chatelier's principle in action. We're adding a product which pushes the reaction back towards reactants. That is to say, in the moments after the SO4 is added, net precipitation occurs. We can actually think about this in graphical form, and this is worth doing. We think about the concentration, for example, of sulfate over time. Initially, we're in an equilibrium state, and so that concentration is constant. When we spike with SO4, we increase its concentration rapidly to a non-equilibrium situation, such that spontaneously SO4 will precipitate out with the barium 2+. Since the concentration of Ba2+ didn't change, this has the effect of depleting the concentration of Ba2+ to a lower level. You can see then that this is a really nice way to push as much Ba2+ out of solution as possible. We're going to end up with a solution that contains a lot of SO4 2- dissolved, but if we don't care about sulfate and what we're really after is the Ba2+ ions, this is a nice way to recover as much barium 2+ as possible. The common ion effect is also relevant when we want to start with a salt, Mx in the solid form, and dissolve it in a solution that already contains one of the ions of that salt, either M+ or X-. The solubility of the salt we want to dissolve will be lower in such solutions. This is consistent with the effect that we just saw, the idea that the reactants will be favored somewhat more in this quote-unquote primed solution which already contains the common ion.